be treacherous in the last possible minute. So today I'm going to tell you about some thoughts that I have about efficient approaches to open many-body quantum systems. And so the first thing that I want to highlight is that also according to this workshop, there is a huge diversity in the type of systems that we as theorists are confronted with while working in this field. Not only huge diversity in systems, but also huge diversity in applications that can range from, quantum computation with neutral atoms, with ions, with superconducting qubits, to quantum simulation, precision measurement, and also, for instance, quantum networks. So if instead of looking at this huge diversity of systems and applications, I think of what is the common issue of all these platforms, I would say that it is the goal. And the goal is that in most of these platforms, we're trying to control large quantum systems. And because we're trying to control these systems, this means that they are naturally open to the environment. And then we have to deal with things like decoherence. And so even if we try to isolate quantum systems maximally, we have the fundamental issue that quantum systems are always coupled to vacuum. And this vacuum has fluctuations. And that's actually very good. If you care about, for instance, generating coherent dynamics between atoms or other type of qubits, you can use these vacuum fluctuations to develop the applications in quantum computing, in quantum metrology, and sensing. So here are a couple of experiments along this line. So the first one is an experiment in a group of Yun-Ye, where they're basically placing the atoms in a 3D optical lattice. This lattice is very compact. The distance between the atoms is sub-wavelengths. And they are able to measure quite precisely cooperative lamp shifts that appear because of dipole-dipole couplings in this lattice. Another recent experiment, or moreover set of experiments, involve realizing spin squeezing in Rydberg atom arrays. And this spin squeezing also arises because of dipole-dipole interactions between these Rydberg atoms. So, coherent interactions mediated by vacuum fluctuations are good news for these types of experiments, but there is always a counterpart to this coherent or unitary dynamics, and this is dissipation. So basically, the fact that these atoms are sharing an environment means that there is going to be correlated decay. And correlated decay can be thought of as a foe or as a friend. So if you care about realizing, metrology experiments, you may want to run your experiment for a very long time. And correlated decay is going to set a limit on that time, both on how well you can, the time you have to prepare your interesting quantum state, and also the time that you have to measure with it. The same applies to quantum computing. So if you have, for instance, you're encoding some computational subspace in some subset of levels of an atom, the fact that there is a phenomena like spontaneous emission means that after some time, you may leak out of this computational subspace. And in particular, if this leaking out is correlated, that can be accelerated. On the other hand, if you may want to, get a lot of photons out of your system, such as, for instance, if you want to build an optical source, correlated decay is actually great. So it actually constitutes the phenomenon in which superradial lasing is based on. And superradial lasing is basically a situation where you pump incoherently a collection of atoms that they are in a cavity, and above certain pumping threshold, they will start to radiate, they will become a source of coherent radiation. And you can actually understand this as a out of equilibrium phase transition. And there are other situations where people have studied out of equilibrium or driven dissipative phases, and they are able to characterize the phase of the system by looking at the density that leaks out of the systems. And so typically the properties of the phases and the thresholds for going across a phase transition depend on the number of atoms. So as a theorist, when you think about how to model these dynamics, you're confronted with the problem that finding exact solutions is still a theoretical challenge. And this is true unless there is a high degree of symmetry. So this is me trying to draw a Hilbert space, generically you'll say that in some extended system without symmetry, there are many possible trajectories in your Hilbert space, and you have to deal with a very large dimension or a set of states. On the other hand, if we have symmetry, for instance, if we place atoms in a cavity, there is permutational symmetry. The set of states that the dynamics explored is much more reduced, and we even know almost kind of by heart some properties of these states because they are easy to compute. So, for instance, here is the decay rate of some state that may scale as n squared if it's basically some set of decay states. So when we think about the problems that Asenjo theorists were confronted with compared to, for instance, condensed matter theories, I would say that, well, they are many-body, and that's true also in condensed matter systems, but typically they involve long-range interactions. They are open, out of equilibrium, and in many cases we care about dynamics. So when you add all these things, the result is that these are hard. And of course, you could say, well, there are approximations, right? So you could think about cumulant methods, you could think about phase space methods like truncated Wigner approximations and so on, but they are limited in, I would say, two ways. The first one is that sometimes they fail. Sometimes they fail in ways that you don't know why they are failing. And the second thing is that in many cases, you can solve for the dynamics at hand, but they may not be able to teach you that much about the underlying physics. So what I'm going to tell you about today is actually, is trying to tackle one of these main challenges in AMO theory, which is to find efficient descriptions of open quantum many-body dynamics. And so maybe this, following with Murray's talk, this is maybe the optimist view. I don't think machines necessarily have to take over. There is still room for theories. And actually, my talk is about how to minimally use machines. Like, I'm going to use machines basically zero, just to check whether I'm correct or not. And most of the results I'm going to show you today are analytical. So I'm going to tell you about two things. The first one is about how to find properties that are general for many systems. And in particular, these properties, the scaling laws with system size of correlated decay. So the way to approach this problem is to not look at solving exact dynamics, just letting go and just be happy with knowing a small degree of information about the system. So if you let go, you may solve a problem that you thought it was not possible. The second thing is to actually use symmetry, and I'm gonna guide you through some results that we have about how to obtain exact dynamics for hundreds of atoms when you can use symmetry in waveguide QED problems, and also how to use correlated decay to do useful things like collective transition quenching, which touches on how to prepare molecules efficiently. Okay, so let me start by the first topic. So the question that I want to answer in this part of the talk is, what is the maximal decay rate of a quantum system? So the goal is I want to find a scaling laws for correlated decay with system size, and system size is n, the number of particles in my system. My hypothesis is that the environment and the arrangement of the particles is going to change these scalings. And the result is that we're going to be able to derive simple universal laws, universal means that are applicable to a broad class of Markovian systems in a way that is easy. And easy here means that if I give you the recipe, you can put it in your computer and the computer will tell you the result in polynomial time. So I'm going to consider some generic Markovian many-body dissipative systems. So, I mean, we're in an AMO theory type of workshop. So typically for us, this may be, atoms talking to photons, but this could be NV centers talking to magnons or something of that sort. It's like broad. I'm going to describe this system with some spin model that is governed by a Lindblad master equation. So we're going to have two parts in my master equation. The first one is Hamiltonian dynamics. And for simplicity in this talk, I'm going to consider that the Hamiltonian conserves the number of excitations. I could relax this, but that makes my talk, easier to give. So I'm gonna choose that. And the second part of my evolution is this dissipator. And here I'm allowing for decay that is correlated because it depends on particle I and particle J via this coupling or dissipative coupling gamma ij. And so this basically tells me about dissipative interactions between these particles, and I can write these interactions in terms of an n by n matrix, which tells me how particle 1 interacts with itself, with particle 2, and so on and so forth. And the only thing that I have to impose is that this matrix is positive semi-definite, and I have to do that to guarantee that I have a reasonable quantum evolution. So basically, such that this is a completely positive trace-preserving map. Okay, so then I can take this second part of the equation and I can massage it by basically diagonalizing this matrix and write this equation in terms of collective decay rates, which are the eigenvalues of this matrix, so sorry, collective transition rates. And because I have imposed that my matrix is positive semi-definite, the decay rates have to be either 0 or positive. And this is because, a system decays at 5 megahertz, not at minus 5 megahertz. And the largest one of them will be gamma max, and it will play an important role because I'm gonna care about what is the maximum decay rate. Now these operators are basically collective ITAMP operators, which are superpositions of sigma minus operators acting on all my particles. Okay, so what I want to know is what is the maximal decay rate. So basically, first I need to define the decay rate. So decay rate is the rate at which my system loses population. So this is the total excited state population, this time derivative, and I put a minus sign. This is the decay rate. Then I can use my master equation to compute exactly this quantity, and you find that it can be written like this. So then if you look at this equation, it actually looks like a Hamiltonian. Even though this is a dissipative process, I can write this as some sort of auxiliary or dissipative Hamiltonian. And if now I want to find what is the maximal decay rate, the question that I have to answer is, what is the largest eigenvalue of this Hamiltonian? And so in some sense, we make a connection now with problems in condensed matter physics, for instance, where we're interested in closed systems to find which is the state of minimal energy, and that obviously is the ground state. Now, for an open quantum system, there is an analogy that tells me that to find the fastest decaying state, which I describe by R star, I just need to find the ground state energy of minus a Hamiltonian. Okay, so then before I get into the details, let me just tell you about two limiting cases that are trivial to solve. The first case is when I don't have any interactions between my particles. If I don't have any interactions between my particles, between my spins, this gamma ij matrix becomes diagonal. And it's trivial to actually find that the maximal decay rate is n times the rate of a single particle, such that the rate per particle is constant. On the other hand, if now I have all the spins at the same point, which may be like there is very small volume, or I have some permutational symmetry between all the spins, now this matrix becomes dense. It's basically a matrix where all the elements are 1 multiplied by the decay rate of a single particle. And this goes back to the problem of decay that's solved in 1954. And we know that the maximal decay rate is given by decay state at half excitation, and it scales as n squared. So now, what if we're not in any of these limits? How does the environment with and the interaction range and the dimensionality of our system, which is all encoded in this matrix gamma, change the maximal decay rate? So I said that to solve for this problem, we just have to map it into solving for a ground state. But I haven't really done that much, because if I think about my Hamiltonian, this amenable Hamiltonian, I can put it in the computer, and I cannot exactly diagonalize this for more than few spins. Even more, I know that finding the ground state of a two-local Hamiltonian is QMA complete, means that it's hard for a classical computer, but also expected to be hard for a quantum computer. And in particular, for atoms in free space, this is an XY model with long-range interactions with an oscillating sign. So it's like a frustrated Hamiltonian, which is expected to be hard to solve. So it looks like I really haven't done much, because I have taken a problem which is hard and I have transformed it into another problem which is also hard. But the reality is that now we can make connections with other fields. And in particular, we can throw all the technology that people have developed to deal with ground state problems to tackle this problem. And so we cannot find the ground state energy exactly, but we can set bounds. So we can come up with an upper bound, which we can do with via variational ansatz. So for us, when we think about the decay rate, it will become a lower bound. But we can also find lower bounds, which will become now for the decay rate an upper bound. And for this, we're going to harness some results from quantum approximation theory, Hamiltonian complexity theory. And so if we're lucky, these two bounds agree, they are tight, and we can find the scaling laws. And it turns out that for a broad class of systems, that's what happens. So then let me tell you how to find these bounds. The first one is the lower bound, which is trivial. I mean, it's just like, half a page of algebra. You can think of some ansatz. The easiest way is a product state ansatz. Then we have to do less math. So you can think of, some superposition of ground and excited state times product state. This is not the best ansatz you can think about. You can massage it a little bit. But when you do that, you find that for systems where there is some notion of translational invariance, or at least systems that are extended and not heavily disordered, what you find is that the bound on the largest decay rate scales as n times the largest eigenvalue of gamma. Okay, so this is the lower bound. So what about the upper bound? So for the upper bound, we do the following. We take our Hamiltonian and we separate it into a diagonal part and an off-diagonal part. The diagonal part is trivial. The off-diagonal part, it turns out that this is just an XY model. Then we care about the largest decay rate, which happens to be the norm of this Hamiltonian. And then by the triangle inequality, this norm has to be smaller or equal than the sum of the norms of these two terms. The first, the norm of the diagonal part is trivial, is n gamma 0. And then we have to set, compute the largest eigenvalue of this XY Hamiltonian. And that I have said that to do that exactly is hard. But it turns out that there is a whole field of people that work on finding good bounds to ground state energies of Hamiltonians using product states. And actually, what we do is we take the result of a recent paper of 2019 by Bravi and collaborators that tells us that basically this type of Hamiltonian can be well approximated by a product state. And the error that you make is the following. So this is the best product state approximation to this XY Hamiltonian, and you pay an error that is a multiplication constant that is a factor of 6. So then you do a bit of math, and in the end, because this is now basically a classical Hamiltonian, you can relate it easily with the largest eigenvalue of this gamma matrix. And so now if we put everything together, we have that both the upper bound and the lower bound scale with this largest eigenvalue of gamma. And so now, except for prefactors that we don't care about, the bounds are tight. So we know that the largest decay rate scales as n times gamma max. And this is universal because I haven't told you anything about the particular system that I'm telling you about, except that is described by this broad class of master equations. Okay, so then let me just tell you why this scaling law is not completely crazy. The first thing is we can check that it agrees with what we knew before. So if we have non-interacting particles, we have again a diagonal matrix. The largest decay rate is, or transition rate is one element, so gamma 0. And so it scales as 1. And so the maximal decay rate per particle does not grow with system size, and R star is just proportional to n. On the other hand, if we go to a cavity, we can very easily write this gamma matrix, and we find that this n-square scaling arises because there is all-to-all interaction. So now this n-square that Dicky found, you can think of it of one n coming because you have n half excitations, and the other n coming from the range of the interactions that are all-to-all. And then one thing that you may have noticed or you may not have noticed is that this scaling is completely unrelated to entanglement. So what this means is you can have an entangled state or you can have a product state. Scaling-wise, they decay exactly the same. So entanglement may appear, but it may appear as a prefactor. When we found this out, we were very confused. But then we realized that you could think about this, at least in the case where you have total permutational symmetry, in terms of the quantum definity theorem that basically tells you that if you have a permutation symmetric state, but you just now look at two particles, the reduced density matrix is basically has an overlap of 1 in the large N limit with a product state. And our Hamiltonian is too local, so it's basically a sum of terms that have support over two particles. So the state may be very complicated, but in some sense, we're just looking at some local part of our state. So entanglement should not matter that much. So here are some connections that have been useful that we have gathered from quantum information community. Okay, so then maybe let's go to systems that we're familiar with. So we're going to consider arrays of atoms in free space. And now we want to use this scaling laws to find the scaling laws for this system. So we're going to consider that you have 1D arrays, 2D arrays, 3D arrays. The interparticle distance is given by this little d. And now the only thing that I have to do is I have to find these dissipative couplings between the atoms that are given by the propagator of the electromagnetic field in free space. So this is trivial. And the only question that I have to solve is how does the largest eigenvalue of this matrix scale with n for different dimensions? And actually this you can do in order n squared or n cubed steps. So this is polynomial easy. You can do even more. You can find this analytically. So I don't want to go through it, but you can find the scalings analytically. And these scalings actually look like this. So the largest decay rate goes as n to the 3/2 minus 1 over 2d. So now you can go and check, okay, what happens if you have, for instance, a 1D array of atoms? So 1D is d equals 1. You get 3/2 minus 1/2. You get n. So basically, even though there is long-range interactions between these particles, 1D arrays behave as if they were non-interacting. And as you start increasing the dimensionality of the lattice, the maximal decay rate increases basically because there is more cooperativity between the atoms. These scalings are also independent of lattice geometry, of polarization, and so on, and they are robust to reasonable disorder. So now you could say, well, this obviously is wrong in some limit, because if now I take my array and I compress it to the max to a volume that is tiny, I should go back to n squared. And if I now take my array and I bring the atoms to 1 kilometer away from each other, then this should go back to n. So this cannot hold what is happening. So to look at the finite size effects, what we did is actually do numerics. So we look at the scaling of this largest decay rate as n to the alpha. We fit to extract this alpha. We do this for arrays for up to 60,000 atoms. This is a scaling up alpha of the maximum transition rate versus lattice constant. So these are very small lattice constants where we should go back to this decay limit. So this means that we should have something close to 1 for gamma max. And here the atoms become non-interacting, so we should go back to 0. And these lines are our analytically predicted expressions. So these are the plots that we found. So indeed, we see that there is a range of interesting lattice constants for which we indeed, for these arrays, we find what we expect analytically. On the other hand, as we bring these arrays to be super small, we recover this decay limit. And when we separate the atoms by a lot, we get that the atoms become non-interacting. This course here looks super sketchy. And this is, we have shaded this area. This is just because here the goodness of the fit is bad. We can actually understand these spikes. So they correspond to basically the fit going crazy because there are unclap processes that contribute to these decay rates. But basically what this means is the trend is meaningful, the spikes are not. Okay, so then we could do similar plots with other type of polarizations or lattice geometries like, hexagonal, and this doesn't change qualitatively. And then, as you may notice, there is a transition between this kind of collective behavior towards non-interacting as you increase the distance. But if this scaling should hold, if you start increasing atom number farther and farther. So if we, instead of fitting up to 60,000, we would fit to up to 600,000, what we should see is that this curve starts flattening. And actually, you could say, at what point do we start to see this flattening? Well, you have to increase the number of atoms proportional to the distance to the 6. So basically, if you separate them by some distance, you have to pay a huge price in terms of atom number to go back to this predictive behavior. And you can also consider what happens in current Rydberg experiments. If we consider optical transitions, current Rydberg experiments have a maximal, you could prepare states with a maximal decay rate that is this one. So it basically is still very close to non-interactive. But if you were to scale it up, or if you were to bring the atoms closer, this thing will start flattening. And so this brings me to some, questions that this work poses. The first thing is that, just as a summary, I should say that you have as you decrease the dimensionality of the array, or you increase the dimensionality of the path, you go from something that is basically non-interacting, so non-interacting atoms, 1D arrays in free space, or actually atoms in any dimension that are just coupled by nearest neighbor interactions. They are all non-interacting. On the other hand, in free space, if you increase the dimension, you will start getting larger and larger powers here, up to the case where if you go to this decay limit, you put the atoms in a cavity, you get your n squared. So this scaling laws set an upper bound to the decay rate of any state, in particular, something that is prepared dynamically. You're not guaranteed to hit states like this, but you will never decay faster than this. And so then some questions that arise are the following. So for instance, what is the impact on this on quantum error correction? So for fault tolerance, you require that the error per operation is below some threshold value. On the other hand, now we have an error that scales with system size. What does this mean? I don't know. This one thing also I should say is that these states, this is a worst case scenario. Not all states, obviously, in the Hilbert space scale like this. Actually, typical states, as in hard random states, don't have a superlinear decay. It's actually just linear. Another question is, what do these scalings imply for driven dissipative phase transitions? So if we take this paper, where actually Murray is a co-author, and you start thinking about what if I don't place my atoms in cavities, but if I now have ordered systems in free space, am I going to be able to have superradial lacing in these systems? And then the third thing is, are we going to have a situation where this correlated decay is going to limit the coherence time of metrology experiments, and for that reason, you may prefer to do your clock in 1D instead of in 2D, and so on and so forth. Okay, so I have a few minutes left, so I'm going to tell you about a different type of topic, which is how to harness symmetry in many body systems to actually do efficient computations. So the idea here is very different. So the project before is, what happens if you have a pretty generic system? Here is going to be the opposite. So the question is the following. We know that if we have a generic open many-body quantum system, if we think about the dimension of the relevant Hilbert space, when we don't have symmetry, typically is unconstrained. So in many cases, we have to deal with this exponential scaling of the Hilbert space, which makes the problems hard. We know, on the other hand, that there are situations where if you have a lot of symmetry, such as, for instance, in a cavity where there is permutational symmetry, you can exchange the atoms. You go to a dimension of the Hilbert space that it scales like n. So the question is there something in between this linear scaling and this exponential scaling? And the answer is actually yes. So actually Murray has a beautiful paper or set of papers about this, as well as others, where they have realized that if you place atoms in a cavity and you also now account for local loss, so loss to free space, which in principle breaks this permutational symmetry, you can still do efficient calculations by enlarging your Hilbert space, and then price you have to pay is a complexity that scales as n-cube. So the question is there something else in between? And the answer is actually yes. In systems where there is partial permutational symmetry, you can actually almost continuously go from here to here. And so what type of systems are these? So actually, these are systems that naturally appear in waveguide QED. So in waveguide QED, we have a collection of spins coupled to a one-dimensional path. The Lindbladian, or the dissipator, looks like this, as I wrote before. But now, in contrast to free space, these elements, matrix elements, they do not decay with the distance. They just depend on the relative distance in this form, so with this cosine function. You can write collective YAMP operators, and it turns out that for a waveguide, you don't have n collective YAMP operators, you just have 2, because the atoms either can emit to the right or they can emit to the left. And so basically, by diagonalizing this gamma matrix, you can find easily your collective YAMP operators that look like superpositions of sigma minus operators with some faces that tell me left is plus and right is minus. So, okay. So generically, if you place all these atoms at random distances, even though you only have 2 YAMP operators, the dynamics is hard. So you haven't gotten anywhere. But it turns out that there are special distances. And these special distances are of this form, n pi over p. So it turns out that if p is 1, this reduces exactly to the Dickey case, and it is solvable, and the dynamics happens in an n-dimensional Hilbert space. What happens if p is different from 1? Well, it turns out that still, the YAMP operators span a closed algebra. And we can prove that the dimension of the Hilbert space scales as n to the p. So what physically this means is that you're going to have a collection of atoms where you don't have total permutational symmetry, but you can still have groups of atoms where there is partial permutational symmetry. And this is because, atom 1 will talk to atom 4 and to atom, 7 at the same way. And the same will happen with atom 2 and atom 5 and so on and so forth. So you can group these spins where you're, like describing them by the position, some external degree of freedom. You can fold this into internal degrees of freedom, and now you have super spins where the internal, the internal degrees of freedom are higher, but the description is much easier, and you can describe this in terms of an angular momentum algebra. And so now you can do calculations exactly. So this is a calculation of a superradiant burst for 15 atoms, which is what we can do typically in our computer without imposing any symmetry, for 30 atoms and for 90 atoms. And you can do this in minutes. So I would say that the exact dynamics now can be computed for around 100 atoms. And this is useful, I would say, because you may not care particularly about waveguide QD problems, but you may care about benchmarking your approximation methods, such as cumulants or truncated Wigner. So this is a situation where you have the exact solution for very large spin numbers. The second thing that I should say is that there is a trick here. The trick is, or a caveat, is that Hamiltonian evolution breaks this partial permutational symmetry in waveguide QD. So you basically have to either consider that this is an approximation or get rid of the Hamiltonian. You can get rid of the Hamiltonian if you have 2 waveguides, or if you are in a ring cavity. Okay, and then the last thing that I want to mention, and it's also about systems with a lot of symmetry, is we're going to consider a situation where we have now total permutational symmetry. So we're going to put our atoms all in a cavity or in a waveguide, but at this special distance where basically the separation between the atoms is a half of the wavelength. Or if they are in free space, they are going to be all in a very, very small volume. And I'm going to tell you that correlated decay actually is very useful when you have a situation where you have competition between multiple decay channels. And now decay channels are going to be internal. So we're going to consider a situation where we have some atom or other type of system with some excited state that can decay into a large set of ground states. So this could be, for instance, for an atom, Zeeman levels, and the set of decay rates can be given by Clebsch-Gordan coefficients. So if I think of just atoms with 2 ground states, I can think of the evolution as a random walk in the Hilbert space. So I place all my atoms initially in the excited state. So I invert the system. Initially, I have 0 atoms in each of these ground states. But now decay is going to happen. And eventually, I go to states where all the atoms are in one ground state or the other, or some other combination in between. So if I think about uncorrelated decay, what happens is that I know the distribution, the final distribution of ground states, and actually this is a binomial, so it's actually trivial to compute. And this is what happens if, for instance, again, you I mean, this is a more technical plot that shows the population density, the probability of finding atoms in some given ground state. And this is basically a Gaussian. And this Gaussian, the mean, is dictated by these natural branching ratios. So again, computing your Clebsch-Gordan coefficients. But now consider that you have correlated decay. So basically, whenever a particle is emitted in some channel, it promotes the others to be emitted in that same channel. So this is like an avalanche now. And when you compute the probability distribution, what happens is that it is completely pushed in one direction, and it also becomes narrower. So what does this mean? It means that the winner takes all. And we can compute analytically what is the mean of this distribution. And it's basically at, all the atoms are in the dominant ground state, except for a fraction that where this error basically scales inversely proportional with number of particles. So this is useful if you care to prepare some state with high fidelity. So for instance, we look at the situation of photochemistry, where you have two atoms that you drive, and then they decay. And when they decay, they form a now bounded molecule, but they can decay into many, many possible ground states. And this, how much of this of the molecules you will find in each of these states will be dictated by the Frank-Condon factors. So what we find is that collective decay actually can act as a catalyst for photochemistry. So here I'm going to show you a plot where this is the population of the dominant ground state, the percentage versus number of molecules. If we would consider independent dynamics, we would always find ourselves parked here. So 55% of the molecules are in the right state. But it turns out that when you have now collective decay, as you increase the number of molecules, they, you will prepare your desired state almost perfectly. This is true only if only if one channel is collectively enhanced, which is actually a result of this paper, but it's also true if there is maximal competition. Even if all of them are collectively enhanced, the winner takes all. So maybe as a summary, let me just tell you a bit about some outlook and open questions. So I found that learning about quantum approximation theory for us has been particularly fruitful. So we were thinking, could we use these ideas to bound other observables that are not just the decay rate, but something that is of interest to you? Again, there are questions on how correlated decay may limit the coherence time in metrology experiments, or how scaling laws are going to matter for dissipative phase transitions. Can we have new light sources? And what are the implications for error correction? I have shown you that you can use correlated decay for almost deterministic preparation of interesting states. And perhaps more provocatively, I've told you about correlated decay, but these laws also apply for absorption. So then you could think about problems of light harvesting, such as photosynthesis or solar cells. Does this matter for this type of situations? So with this, I'd like to acknowledge everybody involved in this work. So actually it's color-coded. So basically, Dariel Abishi, who was an undergrad in my group, who is now at Harvard, Eric, Cosimo, and John contributed to the first project I discussed. And then Dariel again, and Stuart, and Dan and Tanya contributed to the molecule or transition quenching project that I described, and Joseph and Sylvia have led the project on superspins that is still unpublished. Thank you.
Thank you for the very nice talk. I have actually two questions. The first one is, you talked about the critical N for essentially this, in the first part of your talk, the critical N for the systems to behave like they're independent, and that doesn't depend on the lattice dimensionality?
No, it doesn't. Like it's a peculiar case where things compensate. So for both 2 and 3D, it turns out that it doesn't matter. Yes, we were surprised in the beginning. I also cannot tell you exactly why, But yeah, basically the decay rate depends on n, but it also depends on the distance. And then when you factor also that distance in how the atoms are spread out, then there is a cancellation. And then everything depends as d to the 6 power.
And maybe another quick question. So couldn't you also look at the slowest decay rate? Would that?
Yeah, the slowest decay rate in some sense is trivial because it's all atoms in the ground state, so it's 0. But then you could say, well, what about the slowest that is not exactly 0? Then these are dark states. And then this is a bit simpler because, at least I would say in my experience, typically dark states live at low excitation densities. So you can find the scalings when you just look at single excitation manifold, which scales as n. Turns out that the most superradiant states lives at n-half excitation, which is the largest subspace of the Hilbert space, and that's what makes this problem hard.
Thanks for the very nice talk. I had a question about the fact you have the lower limit and the upper limit, both are product state based, right?
Yes, we tried also, so you don't have to, you could use an ansatz that is entangled state, so we did that. And then you can see that only the prefactor changes. And there's another way that we found later. Actually, when I gave this talk, there was somebody in the public that realized that they could find another way to find the upper bound. So we are like writing that up. And that you also don't have to use product states. But what I think is useful here is that only with product states, you can find this scaling. And we have checked that, yeah, entangled states give you the same. Of course, you can choose an ansatz or an entangled state that is like G plus E and all the others in the ground states. Obviously, that won't be a good bound. But yeah, we found good bounds or more or less equally good bounds using entangled states, at least for the lower bound.
Yes, I'm still wrapping my head around that very interesting curve with the decay to the plateau and then the other decay. I don't know, if I'm looking at the demonstration there, I didn't see anything, but that should happen. And then you have this, and you were talking about the distance for the correlation. Have you tried to put those on the topology of a circle or a torus so that you don't have that boundary effect?
Yeah, so I can comment on this. So yeah, natural question would be, what if you now, instead of having like one line, you close, right? Is that going to change? And the answer is actually no. Why? Because there is another way of thinking about these scalings, which is this analytical, eventually I'll get there. Yeah, so you can find this scaling laws analytically. And the way of doing that is to first go to an infinite system. Which, now a chain and a ring are the same. And then what you're going to find is when you look at the decay rate in reciprocal space, so this is the Brillouin zone of a 2D array, okay? You could do the same for 1D. What you're going to find is there's going to be a divergence. So you can find this expression analytically, it's very easy. And you see that when K approaches omega 0 over C, which is basically the light line, you're going to have states that are super bright. So then the trick to get these scalings is that you take K, you approach omega 0 minus some error. And it turns out that when you now try to connect between the infinite system and a finite system, you have to realize that a finite system is just basically providing a grid of your Brillouin zone. So how many atoms you have just tell you how much you're approaching this divergence. So you can relate the error that you're making with the size of the Brillouin zone and n. So then this is what gives me this n to the 4th, which is actually what I showed. And so you can do this for 2D, 3D, and 1D. And in 1D, turns out that there is no divergence. And this is true both for rings and for chains. So based on that, I would say, yeah, it's not gonna change. Like it's not so much an issue of finite size. Sorry?
No, sorry, go ahead.
So it is. So in some sense, this is an issue of how I understand it's an issue of cooperativity or optical depth. So it's a bit like in phase transitions where you go below a critical dimension and basically there is no, fluctuations kill long-range order. Here, this is not a phase transition, but you can think of why is this phenomenon happening, and it is because the atoms cooperate. There is constructive interference, even at the many-body level. And basically in 1D, you don't have enough constructive interference. And as you increase in 2D and 3D, that's true. So yeah, that's the reason. It's not so much the topology. Like, I don't think topology matters particularly here.
Ask a related question. You mentioned that fluctuations are related to this umklapp process.
Yeah.
So
Yeah.
umklapp usually refers to processes which sort of kick you from one brilliant zone to another.
Yes. Yes,
Is
I have a
something that
slide
you see
among
these
the
days.
25 million ones. Yes, here. So this is the same expression that I showed in the previous slide. It's just that there I was hiding something. There is a sum over reciprocal lattice vectors. So in the previous slide, I didn't have that because I was assuming that the distance between the atoms was small enough that then G is very large. And if G is very large, basically, you never hit K0. So then you're like, you can throw this away. But then now, if you basically make your distance very large, now G is basically very small. And so now you start, this is the light cone. So this is this circle where there is this divergence. And now, because the distance is very large, the Brillouin zone is very small. So you can fit the whole Brillouin zone inside this circle. And if you make it even smaller, you would fit it twice and so on and so forth. So what you can do is you can fold. And so you can see that basically, as you are increasing the distance, there is a point where suddenly you have an additional term in this sum. And that goes, the fit go crazy. So actually, even though this looks absolutely super noisy.
By decreasing, you see the noise go down.
No, you have more and more spikes. So when you, there. So even though this looks like this is noise, it's not really noise. This is the first umklapp process, second, third. So we can actually account for all of this. Yes. But it is not meaningful in the sense that, if you add some slight disorder, this will smooth out and you would be able to make this fit correctly. So I would say, again, the trend is meaningful, but the spikes, they point to some physics. It's like physics of crystalline lattices, but they won't be, I wouldn't say that this is particularly meaningful in an experiment.
Any more questions? I should mention that Dana's damper current, what it's shown in your last slide, will be here next week.
I see.
I think he actually will be here for the Charles Regatta.
For the what?
Charles Regatta, the
Oh,
row race.
wow, I didn't
this weekend.
expect that. Yeah, we, so probably if he's here and talks about physics and not only goes rowing, he should also talk about some recent experiment where it's a collaboration where he's seen a self-organization, optomechanical self-organization of atoms in a cavity. So, yeah. Which appeared today on archive. Yes, yeah.
Great.
Thank you.
for joining me. Thank you, Anna. So let's try to get back at 11:15. And coffee is served outside, and